working. We already studied the VGT working, how actually it works. It has a emitter, base, collector. So that we have already discussed. Again, this gives you a flow, kind of flow diagram of the current in the PNP transistor. So we have an emitter on the left side, middle one is the base and last one is the collector. So one thing I need to tell you, sometimes they might ask you which is the largest region, which is the largest region in among these three layers. See, the largest region is usually collector, but when we consider the concentration, it will be emitter. Is it audible?
Yes, sir.
Yes, sir.
Okay. The largest region is collector, but largest concentration is emitter, and moderately is collector, and lightly doped region or lightly doped concentration is base. Okay. Now here we have considered an example of PNP transistor. So now in this there are 5 steps, or we can summarize the working. So these are the main important steps that happens inside the PNP transistor. So when proper biasing is done. Can anyone tell me what do you mean by proper biasing? Biasing means connecting an external supply to the device or a component. That is biasing. What is this proper biasing means? Or can you tell me why the biasing is important? That too, especially in transistors. In the last class, I had told us the different kinds of biasing techniques and all. So why do we need those kind of biasing techniques? We would have just connected our AC supply or the signal which we want to amplify at the input side, and we would have collected it at the output side. But why do we need this extra DC biasing and all?
So to make the base forward bias.
To make the base forward bias. Okay. Fine, but why it is called proper biasing? I mean, why we use this word proper? You have seen the forward, the input characteristics and output characteristics in the lab we have already done. So there you can see the VI characteristics, whatever we were having. Is this input characteristics or output characteristics? Can anyone tell me whether it is the input characteristics or output characteristics?
Output.
Why it is output?
So base we are changing,
Base current we are changing. So for different base current, different waveforms you are getting, and we are talking the plotting is done collector current versus collector to emitter voltage. This is the plotting we have done. To this, we are going to draw a line called DC load line. DC load line. So can anyone tell me what is this DC load line? You have studied in basic electronics first module. This DC load line even comes in diode also. Hmm?
So it gives current and voltage value.
What current is current? It gives the current and voltage value. Which type of current and voltage value? Whether it is an operating, whether it is a normal current and voltage value. So DC load line, it's a graphical analysis of voltage and current which gives the precise values for a component. Or in other way also you can take, it is a graphical analysis of a diode or a transistor which gives a precise values of voltage and current. See this DC load line, we are going to plot like this. This will be the DC load line we are having. So, and we know that there are three regions of operation for the transistor: active, cutoff, saturation. So this region, whatever I am having along x-axis, this is known as cutoff region. So this region is known as saturation region. So the region which is in the center here, this part is known as active region. So these are the three regions of operation. Coming back to DC load line, what does it give? See, this DC load line gives us 2 points. One point along x-axis, one point along y-axis. This will give you the maximum current, maximum voltage the transistor can possess. What is the maximum voltage it can possess? Anyone remember this word called the saturable property? In basic saturable property. These are the basic things, saturable property. It might be an property of an op amp or transistor, anything. If you have gone through my textbook in basic electronics, you might have seen this word saturable property.
So there will be no change current even if you are changing the voltage.
So saturable property will tell it is the plus VCC and minus VEE value. See, in op amp, you know, plus VCC and minus VE you have. If you make this as plus 12 volt, this as minus 12 volt, then according to the saturable property tells that your output swing, the output values, this is positive swing, this is the negative swing. The output swing should be between plus 12 volt to minus 12 volt. If your output raises beyond plus 12 volt or beyond the minus 12 volt, then the output starts clipping. If you have a signal like this and if it is, let us say 13 and minus 13, during that time it is going to clip the signal at 12 at minus 12. So instead of getting a sine wave, you'll get something almost like a square wave. So this kind of clipping of the signal happens when saturation is reached. So this VCE value tells you what is the maximum voltage this transistor can handle. In op amp you have two transistors inbuilt, that's why we take one plus 12 volt, other one minus 12 volt. But in transistor we have only, since it is having only we are talking about one transistor, we will be using plus VCC and other one is ground. So that plus VCC is the saturation point. That means if you use a transistor for an amplification purpose, then if you are given plus VCC is equal to 12 volt, then your output can be maximum 11.4. Beyond this, your output cannot increase. Okay, that value, that maximum range value is given by this point. And what is the maximum current that will flow through this? Is this point. Okay, fine. Then what is this? This is the DC load line. Okay, DC load line gives this maximum voltage and current values of the transistor. Again, this DC load line and this characteristics, whatever we are having, IB with what different IB0, IB1, IB2, IB3, both of them will intersect at certain point. Let us say I have kept the current at IB1. So now I'll be having only this curve. I'll be having only this curve. So I have fixed IB1. So during that time, this DC load line and this curve is going to intersect on each other. Can now someone tell me, now the point of this intersection is in which region? The point of intersection of DC load line and this curve is in which region? Saturation, active, cutoff. It is in which region? Yes. Can you tell me it is in which region? The point is in which region? I told you this region is, this is one region, this is one region, this is one region. Now the point is in which region? Just answer my question. If you are this much silent, it is difficult. Anybody? Kirtana?
So active region, sir.
Then why can't you tell? It is in active region. So now, whenever it is in active region, the transistor, whatever we have used, it will be acting like an amplifier. Why I told all these basic things is, based upon this operating point, you can decide what kind of application you can do. If your operating point is in active region, you can use the transistor as an amplifier. If your operating point is in cutoff region, then you can use the transistor for off switch. That means for switching off some circuit. If you are using this transistor to turn on some circuit, you should make the operating point to reach the saturation region. Okay, so in order to achieve this pointing, this is known as the operating points. This is known as operating point. So since this is known as operating point, so to keep this operating point in a particular or designated region or specific region, we are going to do biasing. Biasing means connecting an external source to a component. So to shift this operating point, we cannot use AC signal. We will be using a DC signal. That DC signal is plus VCC. So by properly tuning that DC signal, we'll tune the current also, collector current. So when you tune both collector current and the voltages, then the operating point will shift and it is going to be at certain zone. So that is known as proper biasing. So now coming back to the working. So here the first step is the injected holes lost to the recombination in the base. See, from this is the emitter side, this is the base and this is the collector. From the emitter side, since it is a PNP transistor, the majority charge carriers are holes. So the current here will be because of holes only. And this is P region, N region, P region. So here in the N type, the majority charge carriers will be electrons. In P type, majority charge carriers will be holes. So when holes are moving from emitter to base, during that time, that holes which are moving from emitter to base is known as injected holes. So that injected holes, injected because they are entering base, so that we call it as injecting. What happens here? Recombination happens. Whenever these holes enter into this base, since it is having majority charge carriers as electrons, some of the holes combine with the electrons. So when they are going to reach when they are going to recombine, the first step, they are going to recombine and we are going to lose some amount of holes. The holes reaching the reverse bias collector junction. So remaining holes are going to reach. This is the second step. Now what happens here, since the output circuit is reverse biased, input circuit is forward biased. Can anyone tell me when I am going to increase more and more reverse bias, what might happen? One thing is depletion layer will increase. Other than that, what can happen? When more and more reverse current is applied, during that time the depletion layer is going to increase. That is one case. Apart from that, the thermal energy will be increasing. That means heat dissipation will increase. When heat dissipation is increased, during that time, the electrons, which are minority charge carriers in P layer, they get excited and they start moving. So when the holes enter to this, the second step, the thermally generated electrons and holes making up a reverse saturation current of the collector junction. So this is the P region. From P region to N region, some amount of electrons, thermally generated electrons will be moving. So this thermally generated electrons are because when you are going to increase the reverse voltage between the base and collector, this gets excited thermally. Now again, the electrons which are supplied, this is the third step. So this is the third step. And in the fourth step, what happens? The electrons supplied by the base contact for recombination with holes. So here in the base, we are having some electrons. They are going to they're trying for recombination with holes. So we got these holes which are which we obtained here. No, those holes will start recombining with electrons. So that is the fourth step. So electron flow takes place because in the N layer. After that, the fifth one, the electrons injected across the forward bias emitter junction. So now what happens? Since it is N layer, the electrons which are in the the base region, they start moving towards the emitter side. So this and this forms the reverse saturation current. Okay, the reverse saturation current from collector to base is because of thermal energy, and the reverse saturation current in the base to emitter is because of the recombination of the holes and electrons. Okay, this is the difference. So this is how actually a PNP transistor works. These are the 5 steps. You have to explain these 5 steps. You can elaborate this based upon the marks. So after that, the comparison, common base, common emitter, common collector configuration. We are, this is what the comparison we are having. When it comes to input resistance, the common base is low, input resistance is low, but output resistance is high. Can anyone tell me in common base configuration, which is that input terminal? Which will be the input terminal of the transistor? In common base configuration, which will be the input terminal? Whether emitter, collector, base. Or which terminal?
Emitters.
Emitter, correct. So emitter is heavily doped. So when it is heavily doped, during that time, whether the conductivity will increase or resistance will increase. In a layer, we are heavily doping it. So during that time, conductance increases or resistance increases.
Conductance.
Yes, conductance increases. So when conductance increases, automatically the input resistance will be low. See, no need of by-hearting anything. Just analysis is important in electronics. In common emitter configuration, again here also it will be low, and in common collector configuration it will be high, because we will be taking the output across emitter, but at the input side we will have collector as well as base, so automatically it will increase. But in common emitter configuration it will be low, because at the input side we have the terminal base as well as emitter. When base and emitter are there, during that time automatically the resistance will decrease, because emitter is having the least resistance. So output resistance. So obviously in common base configuration, we are taking the output across the collector. So when you take the output across the collector, you will be having the high output resistance. And here also in common emitter configuration also we take the output across the collector. So output resistance will be high. And in common collector configuration, we take the output across what we will take. Anybody?
The base.
No. At base we give input. We take the output across collector. Sorry, emitter. When you take the output across emitter, obviously our output resistance will be minimum only, because we are collecting across emitter. And these are all the formulas which you should remember. Current amplification factor. So alpha, beta, gamma. So these formulas, beta by 1 plus beta, alpha by 1 minus alpha, gamma is equal to 1 minus 1 by alpha. These are the relationships between alpha and beta. I mean, they can ask you write the relationship between common base configuration and common emitter configuration. During that time, you can use this. And total output current. So IC is equal to alpha IE plus ICVO. This is the reverse saturation current. This is the reverse saturation current. This is the reverse saturation current. So that will give you total current. So this is the total current. IC is equal to alpha times IE. IC is equal to beta times IB. Along with that, you'll be having some reverse saturation current. That's why we'll just add them. So coming to the phase relationship, except in common emitter configuration, all will be in phase. What do you mean by in phase, out of phase? What do you mean by in phase, out of phase? Everything you have studied, whether you remember or you're not opening the mouth, I don't know. This is the input and this is the output. Input and the output. Okay, this is some circuit. I'm passing this through some circuit. Now, can you tell me what you call the relationship between this signal and this signal, this signal and this signal? See, this is like this. This is exactly opposite to that.
First is out of phase, sir. Second is in phase.
So out of phase means they'll be having a phase difference of 180 degree. So whenever you are having a phase difference of 180 degree, see exactly opposite to this we are having. So this is out of phase and this is in phase. But you see this one, they are in the same phase. So this happens only in common emitter configuration. So amplification, during amplification, the output will be out of phase. That you should remember. And coming to the application, for high frequency application, common base. For audio frequency application, I was telling, for amplifying and voice, all those things, we'll use this one, CE configuration. And common collector configuration, we use it for impedance matching to just balance the impedance between two circuits and all. During that time, we use this configuration. So current gain in common base configuration, it will be less than unity. In common emitter configuration, it will be greater than unity. In common collector configuration, it will be very, very high. Coming to the voltage, common base configuration is high and common emitter configuration is greater than unity, and common collector configuration is less than unity. So usually whenever we want voltage gain, we go for common emitter configuration. Whenever you want a current gain, we go for common collector configuration. But usually we will not prefer common collector configuration. We usually prefer common emitter configuration since its gain is greater than unity. Coming to the next topic, amplification with BJT. So whenever an amplification has to be done, during that time, the transistor should be operated in common emitter configuration. And common emitter configuration, emitter will be common between the input side and the output side. So here you can see the base, between the base and the emitter we have connected the input signal. This is the signal which you want to amplify and give at the output side. So what kind of transistor we are using here? It's an NPN transistor because the arrow mark is away from the base. So from the collector will be connected to the plus VCC. So you can connect that collector like this. You can make it like this also, or if you feel it's confusing, you can connect like this also. Both are same. Okay, no need to worry, both are same. Whether you can just write plus VCC or connecting like this, both will be same. So here to to make the base and emitter to enter into forward bias region, we use this VBB. By applying this DC voltage, we make the base and emitter to enter into forward bias region, because we are talking about amplification. In amplification, the input circuit should be what and output circuit should be what? I mean biasing. We should be forward biased, we should be reverse biased. Hmm?
So can you
So in amplification, which part of, see, this is one circuit and this is one circuit. I have told this is input circuit, this is output circuit. Whether you should make the input circuit forward bias or reverse bias and output circuit forward bias or reverse bias for the application, for this application. For amplification, the input circuit should be forward bias or reverse bias, and output circuit should be reverse bias or forward bias. Amplification means in which region it should operate. Hmm? You're lying lot of things in basics. I don't know. So this is one table which we will study in basic electronics only when you have studied about BJT applications. There was a module called BJT application. So in order to make the transistor in active region, the input circuit should be forward biased, output circuit should be reverse biased. And in order to make the transistor to enter cutoff region, both should be reverse biased. In order to make the transistor to enter into saturation region, both should be forward bias. So now, what for amplification, what you should do?
So for amplification, it should be in
So
active
input
region.
forward bias,
Okay.
output reverse bias.
Yes, good. So amplification means we use active region. So input should be forward bias. So this is positive, negative. This is connected. Base is P layer. So P is positive and this one is connected to the negative terminal because this becomes the common ground. And coming to this collector, it will be connected to the positive of plus VCC and the negative will be connected to the ground. So any of this is common point, we just worry about the collector terminal. This because this is emitter is grounded, so that becomes neutral. So but the collector is N. So N, what we do, we connect it to positive. So now what happens, the other terminal automatically start acting like negative. This thing you should remember one thing. So whenever one of the terminal is connected to positive, other terminal will be automatically, and even though it is connected to the ground, it will start automatically working in opposite polarity. Even though it is connected to ground, it acts in opposite polarity. If suppose in PNP transistor, we have to reverse bias the output, the P, if instead of this NPN, you have PNP. Now P will be connected to the negative and the positive will be connected to the ground. Because when you connect like this only, your output circuit will be reverse biased. So this you should remember. Just a minute. Okay. So this is about the connections, how we are going to do. So now here, since it is in common emitter configuration, can anyone tell me for common emitter configuration, what is the gain formula? Gain means what is the formula?
So I said IC by IB.
That's it. Gain means output by input. If I'm asking for the current gain, it is IC by IB. If it is voltage gain,
VC by VB.
VCE by VBE. That's it. Gain means that's it. Output by input. Whatever circuit they might give you. No need of biarting. Or CE means it is IC by IB, or CB means this one. No need of biarting anything. Output by input. So now here gain. Gain is beta, that is equal to IC by IB. This implies IC is equal to beta times IB. So what is this beta? Beta is the current gain of the transistor. While manufacturing only, this gain will be decided. Okay, whether it is 200, 300, 400, like this. So what is this 200, 300, 400? That means if you use this transistor, it is going to amplify 200 times. It is going to give 200 times the input. And you know, the base current is usually in terms of micro, and collector current is usually in terms of milli. So you can just imagine, micro is greater or milli is greater?
Milli, sir.
Milli. So micro is converted to milli means we are getting amplification. How did this happen? Because of the transistor gain. So when you go to buy a transistor, so they'll ask you how much gain you are expecting. So you tell I need a gain of 100. Then they'll choose beta is equal to 100. That transistor they are going to give. So usually in our lab we use SL100. This is one normal transistor we use, BJT transistor in our lab, or in many of the colleges they'll use. So it is SL100 means its current gain is 100 times, 100. So whatever you give 100 times, it will amplify and give out. Okay, so now the base current which is given here will be amplified and given at the collector terminal. So this is how the amplification happens. And one more thing, some of them have, I've seen a few of the students. So VCE is equal to beta times VBE. See, this is wrong. Why? Beta is current gain, not voltage gain. Please remember this. Alpha, beta, gamma, these are all current gains. This is not applicable for voltage. For voltage, it is just a gain. We tell this gain. Whatever it might be the gain. It might be 10, 20, anything. Okay, but this is the current gain. And why we talk more about current only, why not about voltage here in BJT? Why we talk more about current only, not about voltage?
So BJT is a voltage control device.
You're telling Ulta Roshan. It's a current control device.
Current control device, sir.
Right? It's a current control device. Base current is the one which is going to control your output. That's why we are more worried about beta. But in FET, we will not talk about IG, right? Which is that parameter which we talk about? Hmm? VG, right? We talk in FET, we talk about gate voltage, gate voltage, gate voltage only. We will not talk about IG. IG is a gate current, but we will not talk about that because that is voltage controlled device. So by properly adjusting the base current and properly choosing the transistor, you can get the required the output. So this is the circuit diagram. This is the block diagram approach. So in this, I have just given a small problem. Even I have given in the textbook. I mean, sorry, in the notes. So here you can see that it is 0.05. See the current level and see the current level here. So this is the input and this is the output, and it is amplified 0.05. 0.05 milliampere. If I convert this into micro, what will be the current? If I want to write it in terms of microampere,
Could you repeat the question?
0.05 milliampere, right? If you convert this into micro, how much current it will be?
So into 10 power 3.
That's it will be 500 microamps. See, 500 microamps is now how much you are obtaining here? 5 milliamps. So 500 microamps is converted to 5 milliamps. So by normal formulas we'll be using and we'll be doing it. So after this, next is the construction. This is very, very important. 100% this question will come. And writing this figure is somewhat tricky. You should try to remember. I don't know why they have done this much complex diagrams, because you should remember which all layers comes here, which all layers comes here, and which all layers comes here. It is just like you have seen some biological diagrams, no? Like that cell diagrams and all we used to write in PU, no? The same, it is like that only. So this is the next one. This is BJT fabrication. So I have given the detailed things in the notes, but for remembrance purpose, this is the process flow. Like this only I have given. I have added few more points also. So there are 5 process flows which happens. So there are 5 different diagrams, and these are the important parameters which happens here. Okay, so that will continue in the next class.